Consider the set of numbers 17, 23, 37, 59, and 91. At first glance, they all look pretty prime, since they successfully fail the simple divisibility test for 2, 3, and 5. But as it turns out, one of them is an impostor. 91 isn't prime, rather it's 7 times 13. It's just harder to spot because it's one of only 3 composites under 100 not divisible by 2, 3, or 5. Even still, it's not that hard to factor it by just going through the known primes one by one until you find one it's divisible by. However, this method known as trial division is not very sustainable in the long term. For example, with 40,410,637, you have to go through over 800 primes to prove it's composite. Even with faster tests like elliptic curve prime proving, it can still take ages to definitively prove a number one way or the other. This is where probabilistic tests come in. Instead of telling you a number is definitely prime or definitely composite, they tell you if it's definitely composite or probably prime. These are much faster than deterministic tests, and the probability can be tuned depending on how long you want to run the test. All primes will produce the same result, probably prime, but occasionally composite numbers are able to slip through the cracks and give the same result. These are known as pseudoprimes and are essentially prime number imposters. In this video, we will suss out these numbers and see what makes them so unique among composites. But to understand pseudoprimes, we first need to understand primality tests themselves, and to do that, we need to know some basic number theory. Specifically, there are 2 important concepts you need to be familiar with: greatest common divisors and modular arithmetic. The greatest common divisor of A and B is simply the biggest number that both are divisible by. Now, you could just list out all the factors and find the biggest one in both lists, but there's an easier way to calculate it called the Euclidean algorithm. Basically, from the bigger one, you subtract the smaller one as many times as you can without going negative, then have this result replace the bigger one and repeat the process. Eventually, you'll reach 0, at which point the last non-zero value is the GCD. Also, here are some identities with 0 and 1. If 2 distinct numbers have a GCD greater than 1, then it automatically means the bigger of the 2 is composite. On the other hand, if the GCD equals 1, the numbers are known as coprime, meaning they don't share any factors. While we're on the subject, there's an important function called Euler's totient function. It's denoted phi of n and equals the number of numbers less than n that are coprime to n. For example, the prime factors of 10 are 2 and 5. Multiples of 2 will have that in common with 10, and therefore not be coprime to it. The same applies with 5. So after eliminating those, we're left with 1, 3, 7, and 9. 4 numbers, so phi of 10 equals 4. 11, on the other hand, doesn't have any prime factors except itself, so all positive numbers less than it are coprime with it, meaning phi of 11 equals 10. In general, phi of a prime is p minus 1, and there's a similar formula for prime powers. As for composites, since phi is a multiplicative function, you can split it up using the prime factorization of n, then calculate phi of each prime power using a simple formula, and multiply those together to get phi of n. With this method, we can easily calculate values for the function to get this table or this graph. Now, the totient function might seem like a pretty random thing to care about, but it shows up all the time in number theory, and we'll get to its uses very soon. For now, it's time for the other main concept, modular arithmetic. It said 2 numbers are equivalent mod n if their difference is a multiple of n. But I prefer to think of it a bit differently. The modulo operator from programming languages, a mod n, basically gives you the remainder of a if you were to divide it by n. This is called reducing mod n. We can use it to define that a is equivalent to b mod n if a mod n equals b mod n. For example, 17 and 66 are both 3 more than a multiple of 7, so 17 is equivalent to 66 mod 7. Since any numbers spaced n apart are equivalent mod n, we only need n of them to be representative of the integers as a whole. The term for this is that they form a residue system. When working mod n, we usually choose to keep things within the residue system 0 to n minus 1, which can be achieved by reducing mod n after every step. If you reduce the entire number line mod n, you'll notice it repeats every n steps. Due to this, it helps to think of numbers mod n not as an infinite line, but instead as a finite circle. In mod 7, moving 5 spaces clockwise has the same effect as moving 12 spaces clockwise or 2 spaces anti-clockwise, providing an intuition why 5, 12, and negative 2 are all equivalent mod 7. And moving any multiple of 7 brings you back to where you started, which explains why within mod n, you can always add multiples of n without changing anything. Multiplication is similar. For example, what's 4 times 10 mod 11? Well, if you multiply them, you get 40, which after reducing becomes 7. Alternatively, you could turn 10 into -1, then multiply to get -4, which also becomes 7. Either way, we find 4 times 10 is equivalent to 7 mod 11. It might seem a bit weird to say 7 is a multiple of 4, but that's modular arithmetic for you. Since multiplication is just repeated addition, we can repeatedly move 4 spaces clockwise to find all multiples of 4. Even though we miss 7 on the first pass, since it loops around several times, we do eventually hit it on the 10th step. In fact, we actually hit all numbers mod 11 before repeating the cycle by hitting 0 at step 11. This has major implications. For one thing, it effectively means all the numbers are multiples of 4, so dividing by 4 is actually a defined operation within mod 11. Even though we're stuck with integers, all you have to do is multiply by the multiplicative inverse of 4, i.e. the number it forms 1 with, which in this case is 3. Sure enough, the final equivalence checks out. Another implication is that if we construct a multiplication table mod 11, then the 4's corresponding row and column both have what I'm going to call the Sudoku property, where they contain each number exactly once. But it's not just 4. If you try this with other numbers mod 11, you'll see all of them except 0 have this property. If we fill in the entire multiplication table, then it now has a table-wide version of the Sudoku property, other than the zeros, of course. This makes the numbers mod 11 a finite field, which is a huge thing in cryptography. Anyway, what happens if we switch over to mod 10? Well, if we look at multiples of 4 on the circle, it does loop around once, but by the second loop it hits 0 at step 5, only having encountered half the numbers. Since the cycle repeats so soon, you'll never get a chance to hit the ones you missed. Therefore, not all numbers are divisible by 4 mod 10, and 4's row won't have the Sudoku property. The reason for this is that 4 and 10 share a factor in the form of 2, making them non-coprime. Multiples of 4 are automatically multiples of 2, and since 10 is yet another multiple of 2, subtracting by it to loop around does not let you escape the multiples of 2. Therefore, you'll never encounter the odd numbers. 11, on the other hand, is not a multiple of 2, so when you subtract by it to loop around, it gives you a chance to start fresh and escape the cycle. In general, if a and n are coprime, a will have the Sudoku property and a multiplicative inverse mod n. If they're not coprime though, you'll always be stuck in an inescapable, vicious divisibility cycle. For example, the aforementioned evens mod 10. Since all numbers in the cycle share some kind of divisibility with n, these cycles will never reach numbers coprime to n, including 1, which is coprime to everything. However, the only way to enter such a cycle is to inherit its corresponding divisibility through multiplication. Therefore, if a and b are both coprime to n, they can't possibly be in any of these cycles, and therefore neither will their product. In mod 10, for example, the only numbers coprime to 10 are 1, 3, 7, and 9. Not only do they each have the Sudoku property, but if we isolate the intersection of their rows and columns, we get a self-contained subtable. In other words, multiplying these 4 together won't result in anything outside of these 4. The set of integers mod n coprime to n is known as the reduced residue system mod n. Their corresponding modular multiplication table will always have the Sudoku property, and the cardinality of this group, aka the dimensions of the table, will be equal to phi of n. With that out of the way, we can now take a look at modular exponentiation. Remember, exponents are just repeated multiplication, so if we successively multiply by a, we'll encounter all powers of a. Within modular arithmetic, you can reduce mod n after every step to make things a bit easier to calculate. As an example, we'll look at 6 to the 7 mod 11. 6 times 6 is 3, times another 6 is 7, times another 6 is 9, and so on and so forth. On step 7, we reach our target and find 6 to the 7 is 8 mod 11. But what if we keep going? Well, it eventually reaches every number mod 11 except 0, and then repeats the cycle by hitting 1 at step 10. The main takeaway here is that powers of 6 mod 11 repeat with a cycle length of 10. What about other bases? With some of them, like 7, we do indeed get cycles of length 10, but others, including base 3, only have 5 steps before repeating, meaning they end up missing half the numbers. Then base 10 only has 2 steps before repeating, and base 1 obviously only has 1. We can capture this behavior using a function called the multiplicative order. The order of b mod n, denoted ord n of b, equals the number of steps it takes for powers of b mod n to loop around back to 1. In other words, the cycle length for powers of b mod n. An important caveat of this function is it's only defined when b is coprime to n. To see why, we'll switch over to mod 10. 8 and 10 are not coprime since they're both even. As we've seen, multiplying by 8 will never result in 1 due to the aforementioned vicious divisibility cycles. Well, exponentiation is just repeated multiplication, so if we try to form one of these cycles with 8, this now prevents us from ever looping back around to 1, and so our definition breaks down. But it is still defined for those that are coprime to 10. In fact, as we saw earlier, they form a reduced residue system, where multiplying by these numbers exclusively will never result in something outside of it. Exponentiation by one of them is actually an example of such an environment. Due to this, we can pretty much ignore the non-coprime ones and only focus on the coprime ones, of which there are 5n. In mod 10, the reduced residue system contains 4 numbers, and calculating the multiplicative order for each one, we get 1, 4, 4, and 2. As one final example, we'll look at mod 9. Its reduced residue system has 6 numbers, and the orders are 1, 6, 3, 6, 3, and 2. Laying out the mods side by side, you'll notice an interesting pattern. The order of b is always a factor of 5n. Why is this the case? Well, with 5n options, you're guaranteed to enter a cycle eventually, because at the very latest, after 5n steps, you run out of new places to go, and must revisit somewhere. Furthermore, the cycle must repeat exactly where it started, which is always at 1. If it repeated elsewhere, it would mean multiple numbers times b equal the same thing, but since the order is only defined with coprime b and n, b's row has the Sudoku property, which repetition contradicts. This explains why it's less than or equal to 5n, but why these specific values? To see why, we're going to take the reduced residue system mod 13 and draw an arrow from each one to its value times 5. Even though the cycle with 1 and 5 itself only has 4 terms, the rest of them form cycles on their own. These cycles may be disconnected, but you can actually convert between them by multiplying all the terms by some relevant value. Since you can change between them so easily, all the cycles must have the same length. With 12 options, the only possibilities are 1 12 cycle, 2 6 cycles, 3 4 cycles, and so on, the factors of 12. In general, with 5n possibilities, the cycle length for powers of b mod n must be a factor of 5n. So if x is the multiplicative order of b mod n, repeated multiplication by b will take you back to 1 after x steps. But since it is a cycle after all, you can keep going through it again, and you'll also get back to 1 on steps 2x, 3x, and so on, all the multiples of x. Remember, x is a factor of 5n, which means 5n is one of these multiples of x. Even though the order is different for each number, it's always a factor of 5n, so all of them repeat back to 1 on step 5n. In other words, for any base b coprime to n, b to the 5n is equivalent to 1 mod n. This fact is extremely important in number theory. So important that it gets the honor of being known as simply Euler's theorem. That's right, this is the Euler's theorem. An important consequence is its special case when n is prime. Since 5 a prime is just p minus 1, it means if a is coprime to p, a to the p minus 1 is equivalent to 1 mod p. This is known as Fermat's little theorem. You can alternatively multiply both sides by a to get the more aesthetic version, a to the p is a mod p, but I'm going to stick with the original. With that, we can finally cover our first primality test, fittingly called the Fermat primality test. Given a number to test n, you pick a non-zero base b. You then calculate the power mod b to the n minus 1 mod n. If it's equivalent to 1, you output probably prime, but if not, you output definitely composite. The Fermat test is inherently probabilistic, because although all primes satisfy the equivalence due to Fermat's little theorem, not all numbers that satisfy it are prime. Composite numbers that satisfy the equivalence are known as Fermat pseudoprimes. In the following section, we'll examine these numbers in detail, and after that, we'll take a look at the test's efficiency and accuracy when you account for them. The most famous Fermat pseudoprime is 341. If you calculate 2 to the 340 mod 341, you'll find it's equivalent to 1, even though 341 is composite due to being 11 times 31. The number 2 in this case is known as a Fermat witness, because it essentially provides false witness that 341 is prime. It's also sometimes called a Fermat liar, but honestly I can't blame 2. For all composites less than 341, 2 to the n minus 1 mod n is not equivalent to 1. So why does it give false witness here? Well, it all comes down to the multiplicative order of 2 mod 341, aka the cycle length for powers of 2 mod 341. Euler's theorem tells us the cycle must loop back to 1 at step phi of n. Therefore, the order must be a factor of 300. Indeed it is, specifically 10, but for it to provide false witness, it must also loop back to 1 at step n-1, meaning the order is also a factor of 340. There are 6 numbers that are factors of both, and it's only when the order of b is one of these that it will give false witness for 341. 2 is a witness because its order 10 is one of these factors. But there are several other witnesses for 341, including 15 and 47, as well as anything that appears in their cycles. In total, 341 has 100 bases that are false witnesses to it, while most composites around it don't even have 10. So what's so special about 341? Well, to demonstrate, I'm going to introduce a function I invented called the susceptibility level, or sus of n for short. It essentially represents how susceptible n is to being a pseudoprime. Its definition is as follows. If n is prime, sus of n equals 0. But if n is composite, sus of n equals the GCD of n-1 and phi of n. The reason for the special condition on primes is that otherwise, they would always score p-1 due to the two arguments being equal. But since they genuinely are prime, they can't possibly be imposters, so we just set susceptibility to 0. If n is composite, the two values will not be equal, and their GCD is usually pretty low. With 57, for example, the GCD of 36 and 56 is only 4. But some numbers have an unusually high susceptibility, for example 91, where the GCD of 72 and 90 is actually 18. Another example is the aforementioned 341, where the GCD of 300 and 340 is 20. Looking at the sus of n graph up to 600, we could see they're both pretty high. As it turns out, both of these numbers are pretty common pseudoprimes. In fact, they're actually the first Fermat pseudoprimes for bases 3 and 2 respectively. But why does having a high sus of n make you susceptible to being pseudoprime in the first place? Well, remember, for b to be a false witness, its multiplicative order must be in that intersection of factors of phi of n and factors of n-1. If these two values have a high greatest common factor, it makes them more likely to have a lot of common factors in general. More common factors means more opportunity for the order to be one of them, and thus more chance for b to be a false witness for n. But why are some numbers more susceptible than others? Well, in general, to maximize the potential factor overlap, you want both n-1 and phi of n to have lots of factors. 91 is one more than 90, which has a pretty high relative abundance, meaning lots of factors. Furthermore, its factors 7 and 13 are also both one more than some pretty abundant numbers 6 and 12, which explains why phi of n also has a lot of factors. This results in a high sus of n with a lot of factor overlap, meaning more chance for the cycle length to be one of these, producing a false witness in relation to 91's pseudoprimality. In general, pseudoprimes are often one more than numbers with a lot of factors, and their own factors have this same property. I find this susceptibility function amazing because it's able to successfully quantify a property that seems so unpredictable, and these numbers with high susceptibility will continue to show up throughout this video. Anyway, let's get back to the Fermat primality test, specifically its efficiency. It might seem like a nightmare to do n-1 rounds of exponentiating, but there's actually a trick to make it faster. To calculate b to the x mod n, first convert x into binary. Then you take b and repeatedly square it mod n to calculate b squared, b to the 4th, b to the 8th, and so on. The binary representation of x tells you how to express it as the sum of powers of 2. Due to exponent rules, this will also tell you how to express b to the x as the product of b raised to powers of 2. Since you just calculated those, you can now multiply the relevant ones mod n to get your final answer. This makes finding a to the b mod n logarithmic time instead of linear with the direct method, which is why the Fermat test is even practical in the first place. Of course, with the small examples I've been showing, it's still faster to just use trial division, but that's not the case for long, since these tests are meant for numbers with thousands of digits. So the Fermat test is definitely pretty efficient, but how accurate is it? Well, most composites have very few false witnesses. With 343, for example, only 2% of bases are false witnesses to it, and then 553 has 7%. But something like 481, with its very high susceptibility of 48, has 30% false witnesses. Having a third of bases give the incorrect result is definitely annoying, but we can somewhat alleviate this by simply doing multiple rounds, each with a different base, often chosen at random. Because if there's even a single non-zero base where the equation is false, then n is definitely a composite. Just make sure to not choose 1 or n-1 as your base, since those are always false witnesses. Applying this to 481, you might get unlucky and choose a false witness for your first test. You might even get unlucky several times in a row, but with only 30% false witnesses, the chance of this becomes increasingly unlikely. But that raises the question, how high can this proportion get, and are there any composites to which all bases are false witnesses, making them immune to the Fermat primality test? The answer is yes, with a caveat. They're known as Carmichael numbers and are defined as those such that for all b to the n is b mod n. The first is 561. No matter what base you choose, you'll always end up with b to the n equivalent to b mod n. However, you'll notice this is actually the aesthetic version of Fermat's little theorem, rather than the standard form we've been using. If you switch over to that form, then a lot of these are revealed to not be false witnesses after all. That's because if b and n share a factor, then you'll actually never loop back to 1, as we saw with the vicious divisibility cycles. Therefore, these ones will always correctly tell you n is composite, and it's only those bases coprime to n that are false witnesses. After updating our definition accordingly, Carmichael numbers are much less impressive. In the case of 561, it only has 320 numbers coprime to it, meaning 57% false witnesses, which is much less than 100%. However, there are infinitely many Carmichael numbers, and the later ones can be quite problematic. For example, the 100th Carmichael number, 9,439,201, has 97.8% false witnesses, and this proportion only continues to approach 100%. Clearly, the Fermat test on its own is a bit too susceptible to pseudoprimes. So what can we do to improve it? The first improvement is known as the Euler test, and it's essentially the Fermat test cut in half. So instead of calculating the full power, b to the n-1, you calculate the half power, b to the n-1 over 2. You'll notice it only works when n is odd, but this doesn't matter because you're not going to be testing evens when you automatically know they're composite. Anyway, instead of checking if it's 1, you check if it's equivalent to either of 1 or -1 mod n. If yes, you output probably prime, but if not, n is definitely composite. So why does this work? Well, the full power is simply the half power squared, so if the half power is 1 or -1, the full power will be 1, just like Fermat's little theorem, therefore n is probably prime. In modular arithmetic, -1 will more often manifest itself in the form n-1, but since they're equivalent mod n, they have all the same properties. Now, you're probably familiar with the fact that the only solutions to x squared equals 1 are 1 and -1. Due to this, it seems like the full power being 1 and the half power being plus or minus 1 are equivalent statements with no crossover, making these two methods equivalent tests. But in modular arithmetic, things work a bit differently, and you'll occasionally find other numbers that square to 1. For example, 5 squared is 1 mod 12, despite 5 being neither 1 nor -1. These are known as non-trivial roots of 1, and if the half power is one of them, then the Euler test will tell you n is definitely composite, but the Fermat test won't. The reason the Euler test can say this with confidence is that non-trivial roots of 1 only exist for composite moduli. The proof of this is pretty simple. If there's a non-trivial root of 1 mod n, it means there's an x where x squared is 1 mod n. We can rearrange this to x squared minus 1 is 0 mod n, then to x plus 1 times x minus 1 is 0 mod n. The only numbers that are 0 mod n are multiples of n, so this is equivalent to saying whatever is the value of the product x plus 1 times x minus 1 is a multiple of n. Furthermore, if x is non-trivial, then neither of x plus 1 or x minus 1 can themselves be multiples of n, because that would make x equivalent to plus or minus 1, making it trivial. So the question remains, if a times b equals c, is it possible to have c divisible by n, but neither of a or b? Well, if c is divisible by n, its prime factorization must contain all prime factors of n. If n is composite, you can collect these in two passes, some of them with a and some with b. But if n is prime, it only has one prime factor, which must be collected in its entirety by either a or b, which would then have to be a multiple of n, violating our requirement. Therefore, when n is prime, the only roots of 1 are 1 and n minus 1. So going back to the test, there are now 3 distinct possibilities. Case 1. The half power is plus or minus 1, meaning the full power must be 1, so n passes both tests. Case 2. The half power isn't plus or minus 1, and the full power isn't 1, meaning n fails both tests. And case 3. The half power isn't plus or minus 1, but it's one of those non-trivial roots, so the full power actually is 1. Numbers in this third category fail the Euler test but pass the Fermat test. In other words, this category consists of Fermat pseudoprimes whose compositeness is revealed when you switch to the Euler test, making it a bit stronger. So let's look at some examples. With 91, bases 3 and 4 were previously false witnesses with the full power, but now with the half power, they reveal that it's composite. The same applies to Carmichael 561 with bases 5 and 7, making it no longer invincible. But unfortunately, there do still exist false witnesses. When this is the case, n is called an Euler pseudoprime for base B. They actually form a subset of the Fermat pseudoprimes. For example, 341 and 561 still pass with base 2. Even worse, there are numbers known as absolute Euler pseudoprimes, where no matter what base you choose, as long as it's coprime to n, it will output probably prime. These form a subset of the Carmichael numbers, and the first one is actually the one and only 1729. They're actually half as common as the Carmichael numbers, which is certainly an improvement, but they're still a huge barrier when it comes to finding primes with the Euler test. So how can we improve the test further? Well, this is where the improvements diverge into 2 different tests. On one side is the Solovay-Strassen test, and on the other is the Miller-Rabin test. The Solovay-Strassen test is really cool, but the Miller-Rabin test is both simpler and stronger. It detects all the imposters the Solovay-Strassen test does, and then some. So in the interest of time, I'm just going to go straight to Miller-Rabin, and maybe I'll cover Solovay-Strassen some other day. Anyway, how does the Miller-Rabin test actually work? Well, as I mentioned earlier, the Euler test is essentially the Fermat test cut in half. So what if we were to cut it in half a few more times? Would we be able to repeat that success? The answer is yes, and this is the basis for the test. There are several ways to formulate it, but I'm going to start with the one that I find follows most intuitively. Given a number to test n, you pick a base b from 2 to n minus 2. The first step is to simply calculate the full power, b to the n minus 1, and check whether it's equivalent to 1 mod n. If not, n is definitely composite, which we know from the Fermat test. But if it is equivalent to 1, n could be prime or a Fermat pseudoprime, so the test continues. The next step is to take n minus 1 as a value called x, and repeatedly cut it in half as many times as you can. You then calculate b to the x mod n with all the values, giving you the full power, half power, quarter power, and so on. Based on these values, you will end up in one of 3 possible outcomes, which I think are best explained by starting with examples. So let's look at n equals 1729 with base b equals 2. In this case, the starting value for x is 1728, so we first calculate 2 to the 1728 mod n. It's equivalent to 1, meaning n may or may not be prime, so we have to keep going. Cutting x in half, we get 864, but 2 to the 864 is also 1 mod n. Cutting in half again, 2 to the 432 is still 1 mod n. And this keeps happening for several more rounds with x equal to 216 and 108. But eventually we get 54. 2 to the 54 mod n is not 1 or negative 1, it's actually 1065. But remember, due to exponent rules, 2 to the 54 squared is just 2 to the 108. This means 1065 squared is 1 mod 1729, making it a non-trivial root of 1. These can only exist for composite moduli, so 1729 is composite. In general, each successive b to the x is a square root of the previous one, so if you ever get a 1 followed immediately by something other than plus or minus 1, it means there is a non-trivial root of 1, so n is composite. But this is only one of 3 possible outcomes during this step. The second case can be seen by changing n to 8321. It starts off the same as before. 2 to the 8320 is 1 mod n. Same with 4160, 2080, 1040, 520, and 260. But the next value is 130. 2 to the 130 mod n is 8320, which seems non-trivial until you realize it's actually equivalent to negative 1, so it's a trivial root, which provides no additional information. 130 still has one more factor of 2 left in it, but it's of no use to us. Calculating 2 to the 65 only gives us a root of -1, not 1, whose non-triviality provides no insight since roots of -1 are always non-trivial. So we have to stop here and the test output's probably prime. For the third case, we're going to go back to n equals 1729, but this time with base b equals 9. It again starts just like before. 9 to the 1728 is 1 mod n, and the same applies with 864, 432, 216, and 108. This time though, 9 to the 54 is also 1 mod n, and cutting in half again, 9 to the 27 is still 1 mod n. And at this point, we're pretty much out of luck, because 27 is odd, so we can't cut it in half any more times. We've exhausted all our options without finding a non-trivial root of 1, so the test output's probably prime in this case as well. To summarize the three cases, you basically look at the first thing you encounter after the series of 1s. It could be a non-trivial root, it could be -1, or you might never escape the 1s before hitting a dead end. Having a non-trivial root of 1 mod n proves n is composite, but the other cases don't tell you anything with certainty. There's also case 0, where you don't have any 1s to begin with, in which case n actually fails the Fermat test, which also proves it's composite. And here's a visual representation of the four cases. Primes will always result in cases 2 or 3. Composites will almost always result in case 0 or 1, but they can still result in the other cases, meaning the Miller-Rabin test still isn't perfect. Composites that pass the Miller-Rabin test for some base B are known as strong pseudoprimes to that base, and are a subset of the Euler ones for said base. As we've established, 1729 is composite, which the Miller-Rabin test correctly determines with base 2, but not 9, making it a strong false witness for 1729. The other example, 8321, is also composite, so 2 is a strong false witness for 8321, although this time 9 actually isn't. Also worth noting is that 1 and -1 are always strong false witnesses for n, which is why we don't pick them. These strong false witnesses are certainly annoying, but they're not nearly as problematic as before. In the past, we've encountered numbers where every coprime base is a false witness, such as the Carmichael numbers, but with the Miller-Rabin test, these don't exist. In fact, the proportion of false witness spaces is never more than 1/4, and most of the time it's way lower than even that. This fact makes repeating the test with different bases extremely effective. With that, we can now take a look at how computers run the test efficiently. The inputs are n, the number you're testing, and k, the number of rounds. You start by factoring out as many 2's as you can from n-1. In binary, this is as simple as a bit shift operation. This will result in 2 to the s times d, where d is odd. Then for k rounds, you do the following. Pick some b at random from 2 to n-2. Next, you calculate b to the d mod n. With the method I showed off before, this is actually the last of the powers you calculate, but in practice, it's more efficient to do so in the opposite order. That's because the rest of them can now be calculated with successive squaring. Looking through the results in this order, the conditions are slightly different. If your starting value is 1, then you must be in case 3 from earlier, so you can end the round early and move on to the next. But if it's not 1, you'll move on to the successive squaring part, which will last up to s rounds. If you ever encounter -1, it means you're in case 2, so again, you can end the round early. But if you instead encounter +1, it means you're in case 1, where you found a non-trivial root, so you output definitely composite and end the entire test. And likewise, if you make it to the end of the successive squaring and the value still isn't 1, it means n actually fails even the Fermat test, so you again output definitely composite and end the whole test. After k rounds of this, if you still haven't gotten a definitely composite output, then you output probably prime. Now, there is still the possibility that n is composite and all the bases you tested just happen to be strong false witnesses. But remember, even at the very most, only 1/4 of bases are strong false witnesses. So choosing randomly, each base has less than a 1/4 chance of being a false witness, and the chance all of them are is less than 1/4 to the k. This means with only 10 rounds, you can already be 99.9999% confident in the result, and with 100 rounds, there are 60 of these 9s. Additionally, some bases are known to be particularly truthful. To see why, we'll look at the first strong pseudoprime for each base. A lot of them fail early on, but in practice, you're never going to choose a base greater than n-2. When we adjust for this, the data makes more sense. I'm going to call this the first point of failure function, It's essentially a score of how effective each base is, since a bigger gap before the first pseudoprime indicates fewer of them in general. As you can see, most bases have a strong pseudoprime under 1,000, so they don't score too high. In fact, a lot of them fall into the common traps of 91, 217, and 341. But some bases have a particularly high first point to failure, usually getting caught up on numbers with relatively high sus of n. Now, our very first base, b equals 2, actually scores 2047, which isn't beaten for a long time. Due to this, it's generally a good idea to test with b equals 2 at some point. We could take this idea even further by testing with several specific bases that basically cover each other's weaknesses. For example, 2 and 3 both have quite a few pseudoprimes under 10,000, but the first pseudoprime for which both 2 and 3 are strong false witnesses is 1,373,653, meaning testing only those two bases deterministically tells you the primality of any number under a million, no probabilisticity involved. If you instead use the first 4 primes, then it works with all numbers under 3 billion, and if you use the first 12 primes, the upper bound is 318 sextillion, which is greater than 2 to the 64, so it works on all 64-bit integers. But of course, the only reason we know this for sure is because we've tested all those numbers with deterministic tests, like elliptic curve prime proving. If you're looking for primes in uncharted territory, then unless you're willing to do a ridiculous number of rounds, the Miller-Rabin test can't guarantee primality with 100% certainty. Due to this, you might be turned away from the concept of probabilistic tests in general. After all, the main application of prime numbers is number theory, where we're usually interested in proving things with certainty. However, there exists a concept known as an industrial-grade prime. This is a number that is technically not proven to be prime, but is believed to be prime with such a high certainty that we're still okay with using it in industry. But what is this industry? Well, the main non-theoretical application of prime numbers is cryptography. Much of public key encryption is based on the fact that multiplying 2 primes to get a semi-prime is easy, but reverse engineering that to factor it is not. Even if you incidentally used a pseudoprime, meaning n has a few more factors than expected, it doesn't make the problem of factoring that much easier. And besides, the concept of security in general is inherently based on probabilities, and with the Miller-Rabin test, the failure rate can be made arbitrarily low. The main advantage of the Miller-Rabin test is its efficiency. To demonstrate this, we'll compare it to 3 other tests, specifically trial division, the AKS test, and elliptic curve prime proving. If b is the total number of bits in your input, the time complexity of trial division is O of square root 2 to the b, which is exponential, aka not good. The AKS test is O of b to the 6, which is polynomial time, but still a pretty big exponent. Elliptic curve prime proving is O of b to the 5th, and this 5 can become a 4 if we assume some likely true but unproven conjectures. But the Miller-Rabin test is only O of k times b cubed, where k is the number of rounds. This 3 can even become a 2 depending on your multiplication algorithm. Of course, time complexity doesn't tell you everything, and each test comes with caveats. The AKS test is a galactic algorithm, meaning despite its asymptotic optimality, it has a high upfront cost, so the performance gains don't appear until input sizes way beyond what you would ever realistically use on Earth. Elliptic curve prime proving is a Las Vegas algorithm, which means it gives an answer with 100% certainty, but the time it takes to find the answer can widely vary. In fact, its worst case time complexity is actually unknown. On the contrary, the Miller-Rabin test is a Monte Carlo algorithm, which means it can't always give an answer with 100% certainty, but the time it takes to find the answer is at least consistently fast. But how much faster is it? Well, it's difficult to compare them directly because the use cases are quite different, and there are so many factors affecting runtime, like hardware and implementation. So keep in mind, the following is a qualitative consensus compiling various data sources. Anyway, as you can see, Miller-Rabin is by far the fastest. Since this graph is logarithmic, each vertical unit represents a 10 times increase. With small numbers, Miller-Rabin is only about 10 times faster than elliptic curve prime proving. But with the size of numbers currently used in cryptography, it's more like 10,000 times faster. Even if it takes 100 rounds to tell you n is prime, that's still 100 times faster than elliptic curve prime proving. And remember, the vast majority of numbers are composites that fail on the first round, so in the context of actually finding primes, k equals 1 is a more fair comparison, which is what the graph shows. This result really shows why I like probabilistic primality tests so much. It might seem pointless to not know for sure, but considering the probability of failure can be made arbitrarily low, suddenly the concept of good enough becomes realistically practical. The Miller-Rabin test is extremely efficient as well as simple to implement and understand. If you ever need to write a fast prime checking function that's deterministic for 64-bit integers, 12-round Miller-Rabin is one of your best choices. But as long as we continue to use probabilistic tests, there will always be imposters. Instead of getting annoyed, I think we should appreciate these imposters, because they really help you understand how your tests even work, as well as demonstrate what makes prime numbers so beautiful to begin with. With that, we've reached the end of the video. This video ended up way longer than expected, and I couldn't cover everything, but that's because I really wanted to provide an intuition for the modular arithmetic underlying primality. So if you learned something interesting, make sure to like and subscribe, and feel free to join the Kuvina Discord. Thank you for watching, and I'll see you next time. Bye! Among Us.